Hello, everybody. Good afternoon or good morning for some of you. Let me introduce myself. I am Luca Dotto, Country Manager Western Europe for Hamilton Process Analytics. So welcome to this webinar regarding pH with an external consultant, Fred Schneider. I thank so much Fred because he's speaking from the USA. It's early morning at the moment. Yes, this is a part of webinars that we do in this period to stay close to our customers, even in this lockdown period. The presentation will last around 35 minutes, and after that you are free, or also during the presentation, you are free to write your questions in the Q&A session, which you find at the bottom of your screen. Another technical information, all the microphones are mute. If you want to make a question, just raise your hand and I will unmute your microphone. And that's it. So Fred, here's to you. Thank you for being here.
Thank you, Luca. And thank you everybody for attending. On one housekeeping, if you hear any background noise, I do apologize. I'm actually giving this presentation at the hospital. I just had my second child yesterday, so at the hospital, haven't been able to leave yet due to COVID reasons. No one in the family's got COVID, but just wanted to kind of let you guys know if you hear some background, that is on me, and I do apologize. But I definitely am very passionate about this topic, and I wanted to present this to you guys personally versus any sort of recording. So, and I want to be able to answer any questions you might have afterwards. Within this presentation, it's really kind of the backbone of my company, Morpheus Analytics, with the emphasis, as you can see in the top right corner, of pH. My passion is pH. I have roughly about 10, 11 years experience within the analytical laboratory side, all the way to the process side when I actually worked for Hamilton back in the day. And I found out a lot of commonalities that customers of mine or anybody really regarding the biotech industry was kind of suffering or having issues with. And it's really the relationship between online pH sensors inside like your bioreactors or anywhere in the upstream or downstream bioprocess to the analytical lab, and how to create a root cause analysis quickly and effectively to create a change in your process. These processes are very complex, and any sort of change can have a detrimental effect. So with that said, this is the presentation I've kind of created for all the years of my experience, and I'm going to give suggestions. They're just suggestions. I'm not saying they're the absolute law that you need to follow. It's just kind of what my recommendations are to try to get the best bioprocess performance available. So again, the main topic is truly adjusting sampling procedures to really improve that inline, online pH measurements. With that, the presentation is going to start kind of just on a pH overview. I'm not going to go heavily technical on the pH side of things. It's mainly going to be on the types of sensors that are available out there, but then also how to correct your sampling, specifically on the bioprocess, on the bioreactor. We'll talk about the sampling procedure and how to maintain a sterility and a couple other things. But then once you've taken that sample, how do you properly analyze that sample to make sure that if you are doing, let's say, a product calibration within your bioreactor, that you know for sure that it needs a product calibration? And then other things as well, when you're doing like acid and base addition, are you sure that you're within your range based off your analytical methods that you have? And then one of the big things at the very end of the presentation, I go through a problem-solving checklist, specifically on pH, where you kind of start from the pH meter itself all the way to suggestions of the sample itself. So it's a pretty cool presentation. Again, if you got questions, please let us know. I'll be happy to answer them at the end. The reason why I'm really, really passionate about pH is, as you could see within the bioprocess, there's a lot of areas where pH is utilized in situ, in some sort of vessel or stream. And it's really important, A, that we pick the proper sensor, and then B, that we're calibrating the sensors and utilizing it as it's intended. So in certain areas, you're going to have one type of sensor, and other areas, you're going to have another type. You might have steam in place. You might have some clean in place applications. You might have some autoclavation, but then also you're going to have the laboratory setting as well. And each sensor is really made for specific processes. So for most of these processes, there's not one size fits all or one pH sensor I can say I can recommend. And that's kind of where I'll give you guys the tricks and tips of how to pick the proper sensor, but then also problem solving once you know you picked the proper sensor. So within the bioprocess, I'm going to mainly be focusing on the upstream. The reason why I'm going to be focused on the bioreactor, because this is where you're going to be having the cells, and I feel like in my experience, this is kind of where I see the most issues because you're going to have some sort of medium where you have the cells, and the cells are in this complex matrix. And how you pull a sample or how you're running your critical process parameters is really, really important. So within the reactor, of course, you're going to have some sort of sparging of airflow into a sparger. And then you have your impeller that's basically going to mix everything up. But to kind of control these, you need your critical process parameters like dissolved oxygen, pH, soon to be, really kind of hitting the market is the CO2. I'm hearing more and more and more about CO2. But then also like your pressure gauges, your temperature. But then, really to make these changes, we need to create these samples. So we're going to be focusing again today on the pH side of things, but then how it correlates to sampling to do any sort of product calibration within the vessel. And then once we know that if any action needs to take place, we know that the pH is properly working for like acid and base addition or metabolite feeds. Some metabolite feeds are run based off pH control. So these are the kind of areas where you guys could take the ideas and kind of implement it into your strategy. So I'll start with the actual sampling itself. So when you're actually running a sample, here on the right side are kind of the stages that we utilize when running a sample. So of course, when you're running a sample, you have some sort of lab or area that you're running the sample. So you need to prepare all that media. It could be calibrating everything beforehand. It could be, any sort of chem wipes. It could be your buffers. It could be a cleaning protocol that you have. It could be just literally setting everything up. Then what you're going to be utilizing is the sterilization aspect of it. And with sterilizing, you really want to make sure that you're sterilizing the sampling port as best as possible. Most customers are using a 70% IPA. And I would say the biggest concerns is just making sure that you're keeping that sterile environment. We don't want any sort of outside cells to get in to affect your bioprocess. So really spraying down that sampling port. But once you sample, then you need to prepare the samples, analyze the samples, then of course adjust. So we're going to go through this whole entire process as well. But when you're actually taking that sample, an area that I've found where a lot of customers have some trouble with, or they're not quite sure, is how much purge volume you absolutely need to pull, but also maintaining, volume within the reactor. And that's mainly on the benchtop reactors. Most benchtop reactors, I would say it's like a 5 to 10 mil purge volume. So on the benchtop, like on a 1 liter vessel or 500 mil, of course, you're going to have probably a little bit less than that. But it'd be utilized on your dip tube, so you can easily measure the volume in there, the volume, aspirate some of the product or even water through a dip tube, put in a graduated cylinder, see how much sample or see how much volume is in there. And then usually I'd like to multiply that by 2, so you get about double the amount of volume. So you know that you've really cleaned that line. And then like a 20-liter benchtop, usually it's around 10 mils as well. The dip tubes, are very small inner diameter, so there's not a whole lot of hold up volume there. And then stainless steel, it's usually about 25 to 50 mils worth of purge. You have a lot more volume. I see customers even doing like 200 mils worth of purge to make sure that they have a representative sample. And that's really, really important, because if you're going to be taking a sample and run it on any sort of metabolite analyzer, cell counter, or even a benchtop pH sensor, you really want to have the cleanest possible sample and the most representative sample possible. So once you purge that sample, of course, you're going to collect the sample and basically collect as much as needed for your runs. Most customers, of course, are 5 to 50 mils. You want to try to keep the volume as small as possible because you have working volume you're trying to maintain within your reactor. So just a couple key points. We had a question in our previous seminar just regarding purge volume. So if you have any questions on that, I'm happy to help on that. But regarding process analytics, I'm really going to be focusing on the pH measurement system. So the the process side of things, we're going to fill in a couple of the gaps, but I really wanted to talk mainly about the laboratory pH sensor in combination with the process sensors that you guys have. The laboratory sensor should be the most accurate sensor, hands down, compared to the one that's in process that could be in there for 14 days. The reason behind it is because your laboratory sensor, you're calibrating it that day, and you should be able to get real-time measurements very, very fast. But there's a ton of different options out there. There's literally thousands of pH sensors out there, and how do you know which one is the correct one? So I'm just going to kind of give you guys a run of the mill of what type of sensors are out there and some ideas of that I recommend. But really, at the end of the day, don't be blindsided by manufacturers out there that might have a sales team or technical team just saying, "Hey, this sensor works for 90% of applications." The problem within the biotech or any sort of industry trying to sell pH systems is that they really don't understand your process, and they just kind of give you a sensor off the shelf. So it's really important for these manufacturers to ask you questions based off what your process truly is. Is it heavy chemicals? Is there a lot of protein in your process? Is it a viscous sample? These are all big questions to know. And then, like, how many samples are you going to be doing a day? Can that laboratory sensor hold up to that? So within a laboratory pH sensor, you have two main versions. One is a combination electrode, and the combination electrode is kind of what we see here. It's where you have a reference wire. It's usually a silver wire or some metallic, and then you have a sensing electrode as well. So um, this is what we see here. Some of the customers that I've actually seen actually have used some half cells where the reference and the sensing components are actually split. Um, but with this, to create a proper pH or a millivolt value that a pH sensor does create, you solution, which is normally like a 3 molar silver chloride. You need an outer fill solution, which is usually a silver chloride or potassium chloride. You need a specific junction, so we're going to talk about junction material. And then, of course, the sensing bulb, the one that actually measures that hydrogen activity. So all these items are very, very, very important regarding picking out any side of pH sensor. And I'll talk about each one of those kind of in detail. Um, Regarding the pH system, really there's so many different options out there. So really looking at the specification sheets are really important. Can it handle SIP? Can it handle autoclavations? What is the autoclavation shift? What kind of chemical stability does it have? What kind of temperature does it have? These are all things that we should all be aware of for kind of like the quick check mark. Yes, my sensor can do that. Let's move forward. The glass side of things is probably one of the easiest things that you could choose for a pH sensor based off what your process is. Within that, now the reference is the second most crucial decision in my opinion. Um, there's two main pH systems out there. One is what you see here on the screen is a single junction sensor. The fill solution on this sensor is a silver chloride. So if you have a refillable electrode and it's silver chloride, I totally recommend throwing away that electrode. It's usually a very low cost type sensor. The reason why I say throw this out within the bioprocess is the biggest disadvantage is any sort of tris, sulfides, or proteins deteriorate that silver wire and actually wrecks the whole reference system. And I'll show you an example. But a lot of my customers have utilized this sensor because it's the run of the mill, a good precision sensor for like a water wastewater stream that doesn't use proteins, tris, or sulfides. And they think, well, it works good there, it should work well in our application. And that's just not the fact. So this is kind of what the single junction sensor kind of looks like. You have your silver wire here. You have some sort of electrolyte, usually a silver chloride, 3 molar, 4 molar, based off whatever manufacturer you're utilizing. Then you have some sort of liquid junction. So what happens is at some point you're going to have process come into your sensor. And when that gets into your sensor, the reference electrolyte has now been compromised. Not just only compromised, but tris sulfides and proteins deteriorate this silver wire where now your reference is not reliable anymore. And this is why we recommend throwing away this sensor specifically for biotech applications. So again, if you have a sensor that's got silver chloride as any sort of the reference filling solution, again, I highly recommend replacing that into a what we call a double junction sensor. So as you could see, compared to the other example, here is a silver wire sensor filled with 3 molar KCl. It's a tube within the sensor itself, and it's protected. So once you have some sort of process or medium come inside the sensor itself, it's not going to destroy the sensor, nor is it going to destroy the reference concentration in there. So you're still going to be receiving representative samples, and you're not going to get the degradation of the tris sulfides or proteins within that silver wire because it's protected. I highly recommend utilizing a double junction electrode regardless of applications, but you know, they are a little bit more expensive. There's a little bit more manpower that is needed to create them, but they will last you a lot longer. So the fill solution for this would be a potassium chloride. And then with the actual type of sensors, we're actually going to talk about the outer material of the junction. So that's actually right here on the sensor itself. It's going to allow the outer fill solution to leach out of the sensor to attach to the sensing bulb as a salt bridge to make sure that we have the interactions between the hydrogen activity and actual our internal reference, and to create the best possible millivolt signal where then you guys can do your product calibrations. With that, there's 3 main types. There's the wick, the ceramic, and open. And I'll talk about each one of those pretty quickly here. So with some of my colleagues, they know this example, but the wick junction currently is a picture here, and it's basically this fibrous material. It's a wick like you would see in a candle, or and I don't know if everyone on the call understands like a tiki torch, but it's usually some sort of vesicle of like oil, but we could use a candle for an example for this. But within this, you have this filament material that absorbs the potassium chloride or silver chloride solution and basically becomes saturated at the end. So this is internally in the probe, and then there's a small little fibrous material outside, and this is the leaching of the potassium chloride, and then that connects the salt bridge to the sensor itself. With this, it's really just that fibrous material. The advantages are just really for any sort of aqueous type sample, But when you think about a wick junction, high particles or viscous material will clog this specific material. So I always say, like, as a tiki torch or a candle, think about putting mud on that candle or on that wick of that tiki torch and trying to light it. It's not going to light just due to the fact that it's now been covered or coated. And that's just like a pH sensor. pH sensor, it might work right out of the box, very good, because it's not been coated. But once it's been in process for a couple times, now your interactions with the sample is going to be deteriorated, and you're not going to get that representative sample anymore. And then just think about if you're doing any sort of um, process product calibration in the internal pH sensor, and you're utilizing this sensor specifically, that might be a slow responding sensor due to the wick being coated, you're going to have some false calibrations or false stabilities, and then you're going to have a detrimental effect on your inline pH sensor, but you might not see that because the inline pH sensor is performing optimally, but you've changed that with that product calibration. So from the wick, we have the next type of junction. It's this little tiny circle here. It's the white circle. My laser pointer is right over it, and I'm just removing it now. It's a ceramic junction. It's basically a porous material, wood or Teflon or mainly ceramic. And the advantage of this are basically it's an all-around, all-purpose junction. It's basically suitable for most lab applications. Um, but within the biotech area, it needs a high level of agitation. So what's nice is these sensors are really, really good for the bioreactor, because you have a high flow of agitation where the sensor is inside and you're having that agitation where it's going to be basically self-cleaning that junction, because you have pressure internally in the probe and it's leaching the potassium chloride out of there. But in terms of a grab sample, where your sensor is going to be in this 50 ml conical tube, let's say, agitation is very minimal, and these type of sensors actually do clog very, very easily without any sort of agitation. So my next type of sensor that I do recommend, and I recommend fully for the biotech laboratory side, would be what we call as an open junction. Now, the open junction is a laser drilled hole, or what we call as a grounded glass sleeve, where actually the junction is all around the glass bulb on the top. So it would be kind of, on this example, like right around here. And with this, basically the advantage is it's never going to clog, because it's usually going to be some sort of flushable or a high flow rate of electrolyte that's coming in there. One of the biggest disadvantages is you're going to have a little bit of lower overall life, because your internal reference, that silver chloride will leach out a tad bit faster, but it's also higher maintenance. So if you have a lot of people that are doing laboratory work or taking a sample from the reactor and running it on a pH sensor, this might or might not be the sensor for you, because it is very high maintenance compared to the ceramic junction. And here's a cross-sectional view of the two types that I recommend within this industry. As a within this, you have a single open junction, or this can go all the way around. This is again a cross-sectional view. You have some sort of electrolyte that's inside that's going to leach out of the sensor, and again at a higher flow rate. And then you'll have another one that's the ceramic junction, where the ceramic junction basically absorbs the porous material of that ceramic. And then the electrolyte, since it's being absorbed, will be pushed out, because the pressure inside the sensor will be greater than the sample. So it's going to push out that electrolyte out there. But we really want to make sure that the level of the ceramic junction and the open junction are high enough where you never get any sort of ingress from the process into your sensor. So there's two main types of pH sensors, well, of the body itself. So we've talked about, of course, the glass material. There's a bunch there. the actual reference. You have the wick, you have the ceramic, and you have the open. Now we have the body itself. So we have two classes: a refillable and low maintenance gel filled electrode. And here are the differences. The low maintenance gel electrode, it's really rugged. But the two main points that I really wanted to point out is the precision is maximum 0.05 to zero point 0.1 pH units. And then a lot of people really don't understand why it's only about, on average, a 6-month life. And the reason behind that is you can't add any more refillable solution into the sensor. So once that potassium chloride has been depleted, the sensor now cannot create the proper salt bridge from reference to sensing bulb. But it's also a very slow responding type sensor. So within the bioprocess industry, or even in the bioprocess, we want to make fast and accurate decisions. And this is just not the type of sensor that we would recommend for what you guys need. So the refillable electrode itself is a higher maintenance type sensor. But again, if we're creating this process and it's thousands, tens of thousands, hundreds of thousands of dollars of a process, and we have a critical process parameter like pH, we need to make sure we're doing right by us and our customers and our company. And a refillable electrode is a must, in my personal opinion. Again, it's a higher maintenance type sensor, but your precision basically gets cut in half to 5-fold. And again, this is just on the pH side of things, and I'll talk about error and accuracy and all that. But you could handle a lot longer or larger applications. You could also have a glass or epoxy body. So just because it's an epoxy body on a low maintenance sensor, you could also have a refillable epoxy as well to help you with any sort of pH breakage. But here's the big kicker: you're going to have roughly about 1 year minimum life. So a low maintenance sensor, you're getting an average a 6-month life, while on a refillable sensor, you're most likely going to get over 1 year. And then, of course, you're going to have some sort of replaceable fill solution. And then, so now that we've picked our proper sensor, or you understand what type of sensor you have, the next one would be, okay, how do we properly calibrate? Calibration is the second area or it's close to the first, where I see a lot of issues or a lot of additional errors that can be fixed. And the areas that we really want to choose on is how we actually do the calibration. So one of the first things is we really want to use 2 buffers. You don't want to do a calibration with just 1 buffer. But then also, after you do your calibration, you get your slope, you always want to do a calibration drift check. And so like if you did a 4 and 7 calibration and your last calibration buffer you used was 7, you want to go back to 4 and see if the sensor can actually calibrate, or not calibrate, read that 4 buffer correctly. If it can't read your 4 buffer correctly, do you think it's going to read your sample correctly? A lot of customers of mine aren't doing this step. They are now, hopefully, after I've given these talks. But this is a critical part in my understanding of pH. Again, these are standards. The sensor should be reading these standards very, very quickly. And also, we always want to make sure that we bracket these buffers. So if our sample that we're expecting is going to be, let's say, like 6.28 pH units, we want to do a 4 and 7. We had a question from the previous presentation, and they asked, well, what if I'm doing my sample at pH 3? Should I do a 4 and 7 calibration? And you can do a 4 and 7, but you've added additional error because you haven't bracketed that expected value. So basically the slope that you're utilizing could be a little bit off. I can't tell you how much it's going to be off. That's the problem with pH. It's a theoretical measurement. But if you bracket the range, so use, let's say, like 1.68 to 4, you have a better certainty that you're working correctly, or your sensor is working correctly. And I wouldn't go any further than 3 pH units apart. So with your buffers like 4 and 7, there's a reason why the industry is mainly does a 4, 7, 10 calibration. You really shouldn't be doing like a 4 to 10 calibration and say, well, it's bracketed. You really want to be only about 3 pH units apart, because each pH unit is 10 times more hydrogen activity. So you're going to already have a high concentration range or activity range from 3 pH units being 1,000 activity units or concentration of that hydrogen activity. So that's just a quick rule of thumb on that. But then also we want to track our calibration slope daily. So on the laboratory side, we really want to make sure that we're tracking that, because that's going to tell you the degradation of the sensor based off the theoretical value. And then I always get the question, how often should I calibrate the sensor? Calibration really kind of affects everything, and that's something that you're going to have to determine. But one of the things I always tell customers is throughout the day, just put your laboratory sensor back in a buffer just to check to see if it's reading correctly. If it's not, then you might need to do, well, you definitely need to do another calibration, because again, the pH sensor should be reading. So it could affect your electrode type if you're using a wick junction that's slow responding. Your sample could be viscous and making a physical change on the sensor, or it could be abrasive type sample where you need to calibrate because the glass has been abrased a little bit, or it's interacting with the hydrogen ions a little bit differently. Or if you just have a sure number of samples, that alone might need a additional calibration throughout the day. But if you're using the laboratory pH sensor for anything, it should be calibrated that day, not the previous day. And then to follow up on that, when you're actually doing the calibration, it's based off a theoretical equation called the Nernst equation. And I wanted to give you guys an example of what the slope actually represents. So in this example, we're doing a 2-point calibration, a 7 and 4. We're placing the sensor into 7. We get it reading on our laboratory meter. It says stable. We lock it in. It's negative 10 millivolts, or on your meter, it might just say 7. And then we have, we rinse it with deionized water. We blot it dry. Then we place it into pH 4 buffer, and it's reading 150 millivolts. And we hit, the meter says stable. We lock that value in. Of course, it's going to say 4. So what we want to do then is take the difference between the two measurements. And that's where we have 160 millivolts from negative 10 to 150. From there, we want to divide that by the theoretical value. So the theoretical value in this example, each pH unit is roughly 59.2 or 59.16 millivolts per pH unit at 25 degrees centigrade. When you increase or decrease temperature, this value changes. But since we're moving 3 pH units apart, that is a total of 177.6 millivolts roughly. So that's 59.2 times 3. So from 4 to 7, that's 3 pH units. You multiply this value by 3 to get your theoretical voltage. So we're actually looking at how is our sensor interacting with known standards to create or to compare it to the theoretical value. So in this example, if you take this number, multiply it by 100, you get 90%. And I have recommendations on that. But one of the big key areas that I stated was at 25 degrees centigrade. So temperature affects basically everything. That's why we measure it. It affects your electrode, your buffers, your samples. And how do we measure temperature within the process, within the pH meter? Some sensors might be what we call as a triode, where it's a double junction sensor with a temperature probe built in, like an ATC sensor. Some laboratory bench meters can actually test the resistivity of the glass to see the temperature changes, or using an external temperature probe that's attached to your meter as well. And within temperature, the big things that I really want to talk about is at 25 degrees C, we're at 59.16 millivolts at theoretical. So if we get 100% slope, we're on this trend at 25 degrees. But as you can see, if we increase our temperature by 25 degrees centigrade, we now are at 64 millivolts per pH unit. And the further we get away from 7, the greater temperature effect has on your process. So if you aren't using an ATC probe within your laboratory setting, you absolutely need to, because you're adding additional error that you don't have to, or that you shouldn't be having. Also, within the temperature as well, we want to really make sure that we're taking a look at everything together. The closer you are to 7, the less impact, but there still is impact. And we really want to make sure that we're understanding what that temperature has as an effect. So where we can see this is within the buffers. So within the buffers, you have your buffer sets here, usually like a NIST certified buffer. You have, let's say you do your 3-point calibration, your 10, 7, and 4. Within the bioprocess, we always recommend running your samples at the same temperature as your process. So if your process is at, let's say, 36 or 40 degrees centigrade, your pH sensor should be at temperature. This is a term called temperature hysteresis, where it's the heating and cooling down of a material. And even though the probe might have an ATC probe or a temperature probe on there, the actual sensor needs to warm up. So within this, we need to make sure that our meter is calibrated properly to the temperatures, so it's reading temperature correctly. But then it also can utilize this temperature chart for changing the millivolt slope in the actual meter. So if we're running our buffers and our samples, let's say at 40 degrees C, we can look at something that on a buffer bottle, it might say 10.01. But if we move over to 40 degrees C, we're actually at 9.89. So we've added, 12 units or 12 hundredths of a pH unit off. And then if we did the same thing with 7, we're at 6.97 instead of 7.00, and then 4.03 versus 4.01. And since this is a logarithmic scale, the more error you add to the system, it compounds on one another. So always make sure that your meter can read these NIST certified, and then also make sure that you understand the temperature chart as well. So NIST buffers are only certified at 25 degrees centigrade. So make sure that you're running these temperature charts as well. If you need help on that, I can absolutely help you. But also this is in effect for samples as well. So within cleaning, I have some options for you, but really at the end of the day, you need to understand when to clean your sensor. And this might be a very tight range for an ideal slope, but again, your process is expensive and the laboratory probes are pretty inexpensive on a day-to-day basis. And what my recommendation is 95 to 102 would be my ideal range. If it's within that 92 to 95%, I would definitely want to do a cleaning protocol. And I have a couple on here, but I'll definitely recommend the manufacturer's cleaning. They know their sensors inside and out. Unlike myself, I don't build any manufacturer sensors. And then if the process is below 92, of course, try a cleaning, but a lot of times when it's below that 90% mark, it's not going to get back into that 95%. So you would replace that sensor. I was actually one of the type of people that would keep sensors for a long period of time and wish and pray at some point that these sensors would get back to that 95% slope, but they never will. And especially if they're a gel-filled electrode, non-refillable, they're not going to get back there. And then check your response time on your sensor within buffers. A proper working electrode should be stable within 30 seconds. If it's not, you have a slow responding sensor, but again, if it's taking 30 seconds for your electrode to become stable, it's going to take that as a minimum for your sensor to be stable in your samples. So again, these meters only measure a rate of change of millivolts. So if you have a slow enough responding sensor, you're going to get false stabilization errors on your meter, and you might say, "Oh, everything's all good." But if you keep that in if you keep that probe in your sample, it could be drifting for, you know, whoever knows how long the sensor is lasting. And then, of course, check the precision. After a couple samples, check the precision, you know, go back into pH 4 buffer or 7 buffer, and then go back and forth on the 4 and 7. The sensor should be recording based off your standard operating procedure. If it can't, then you know you need to do a recalibration. Also, a nice little quick check is sometimes some of my customers keep the sensor in, let's say, pH 7 buffer for a couple hours, and they want to just see through the day, since it's in that buffer solution, is it drifting? Is it reading 7.4, 7.04 throughout the day and drifting higher or drifting lower? And that's a quick check to see if you need to do a calibration. Also, within their storage, the biggest thing within storage, never store it in deionized water. It's probably one of the biggest things that I see that kind of deteriorates on the sensor, is it dries out that sensing bulb. But really just store it in the manufacturer's storage solution. If you don't have any storage solution, you could put it in usually a 4 or 7 buffer with added a little bit of potassium chloride. For longer term storage, make sure you fill the electrode filling solution, but then also store with a protective cap so you don't have any leaching of the sensor coming out. It'll last your sensors a little bit longer. And then I have a couple cleaning solution ideas that might work for you, but again, I really recommend that you clean the sensor based off the manufacturer's recommendations. But if you don't have any cleaning protocols, you know, for the biotech industry, you have protein. So like a 1 or 2% pepsin in HCl will definitely work. You heat it up to, you know, 50 degrees centigrade and go from there. Bleach for disinfecting. These are a couple protocols that I've used back in the day, and they work very well. But you know, definitely use the manufacturers first. And then, of course, just some general cleaning. This presentation will be online as well, so you can definitely take a look at these. Um, but one of the big things that you could see if your junction is not clogged is seeing if you have any observation of crystals forming. This particulate around the junction. It's really important to see that. That's a good symbol. That means that electrolyte is leaving the sensor. And then keys to accuracy, again, we want to make sure we're using accurate buffers. I can't stress that enough. 4 and 7, after you open, usually expire 3 months after opening. You're still going to have an expiration date that might be a year or two in the future. But after you open, most buffers have like an open area, like a slot where you can put the date, or if it doesn't, always write the date and then cross off the expiration date and put a new expiration date for 4 or 7, 3 months later. 10, absolutely 1 month is the longest it's going to last after being opened. The CO2 in the atmosphere goes into the buffer. It buffers for, you know, a certain amount of time, roughly about a month, but then it's just not as accurate as we need. But also make sure you're using fresh buffer for each calibration for the day. I see countlessly in the industry where we see customers put in buffer in a 50 ml conical tube. They do their calibration, they twist the conical tube cap on, and then they use that for the next week or months or, you know, who knows how long. Again, these are buffers, these are calibration solutions. For most other applications, you know, you use for any sort of analytical devices, usually throw away standards after the day. You should do that here with your pH buffers. And then always with your refillable electrodes, make sure you're using the proper fill solution, but then also making sure that you're not seeing any sort of crystallization inside the sensor. This is what we call a super saturation. But make sure that you're replacing the fill solution of your sensor on a weekly or minimum bi-weekly basis. Most people are not doing that. So when you're running the sensor with the fill hole open, some of the potassium chloride is actually going to evaporate. And then when you add more fill solution, you're going to now have a higher concentration. And at some point, you're going to have crystals form there. And it's a pain to clean that out. So take a Pasteur pipette, put it in the sensor, suck the fill solution out, and then put some brand new fill solution in there. And that's a quick and easy way. And again, make sure you're using the proper fill solution. So if it's a single junction sensor that I don't recommend, that's going to be a silver chloride. If it's a double junction electrode, that's going to be like a 3 molar potassium chloride. And this is where I really like within the presentation, the troubleshooting. So if you see any of these issues, slow responding, or you have the sensor in like a 4 buffer and you start seeing it drifting high or low, or you're running the buffer check and it's inaccurate, it's just not reading correctly, you can actually go through this checklist that I think for myself, when I'm at customers, this is what I do, is this troubleshooting sequence. So I'll go through all these just really quickly. So within first, we want to check the meter. Within the meter itself, most laboratory meters have some sort of back end. It's a B and C connector, but they usually have this cap on the back end of it. And a lot of people think it's for like shipping or moving the meter around, and that's not the case. It's actually a self-diagnostic test. You want to plug that in, again, only when you're seeing issues, and you want to plug that in, and it should short out that meter out. And we want to see 0 millivolts if your meter is accurate enough where it actually shows you the tenths. We want it to be no more than plus or minus 0.2 millivolts. But again, this is a self-diagnostic test. It takes literally 10 seconds. You unplug your sensor, plug in the shorting out cap, and you're good to go. So if that clears, then check your buffers. That's again the next and easiest thing you can do to actually see what's going on. So maybe someone did a calibration. You should log the lot of the calibration that you're using within the slope that you did, but then also see if your buffers are expired or during calibration, did you stir the buffers? But then also installation. Installation is absolutely critical. So if you have your pH solution or pH sensor that's not in solution, you're not going to get an accurate pH measurement. So within process, like with utilizing a connector into a single-use bioreactor, you really want to make sure that the pH sensors are inserted all the way into the bag. So within this cross section, these sensors are not. We really want to see the junction itself, that ceramic junction or the open junction, have product contact. So within this example, we don't have that. The sensor is not fully inserted into the process. So we're not going to have accurate pH readings. We're going to have inaccurate. It might be a precision shift or it might be just a lag response. And here's a quick tip that might help you guys out in the future. So within this type of connector into a single-use bioreactor, there's a logo. If you insert the sensor into the bag and that logo is not covered, that means that the sensor has not been inserted all the way. This is what it should look like. You should basically cut that logo in half, and more than likely that sensor has been fully immersed into the product. And then, of course, just general troubleshooting of the electrode. So make sure you clean the junction, you use and replace the fill solution. But one of the things that people don't realize sometimes is make sure you uncover the fill hole for the laboratory probe when using. So when you're calibrating or measuring, that fill hole should be open. So I always say it's kind of like we want the gravity to basically do its magic. So if you put, like, let's say for instance, like a straw in like a bottle of water, and you put your thumb over the straw and you lift the straw out of the cup, the straw stays in that, or the water stays in that straw until you lift your thumb out. And that is basically what goes on with a sensor. Is we need a gravity to push or create pressure at that junction site to create that proper salt bridge. If you have that fill hole closed during calibration and measuring, you're not going to get the proper salt bridge needed, and you're going to have inaccurate measurements. And then this is probably one of the areas that most customers say, hey, I can do or I can't do, but also proper sample preparation. You need to stir your samples if at all possible. But then also the sensor needs to be fully immersed in the solution. It needs to, the junction needs to be fully immersed, but it needs to be suspended. So within calibration or measuring, do not place the sensor on the bottom of your conical tube. It should be held within the solution without it touching anything around. I see it every day where I see people just put the sensor all the way down to the bottom, walk away and, come back and say, oh, okay, it's 6.2, and they take that measurement. You need to run the samples just like your you got to run your samples in some sort of an agitated fashion, but in suspension. But then also you need to treat your samples and your buffers the exact same for highest accuracy possible, for the least amount of error. You're getting rid of that whole temperature hysteresis that I mentioned earlier. So I know it might not be practical in some applications or in some laboratories or in some production suites, but I highly recommend your sensor be at temperature of your samples. And your samples should be taken right from the bioreactor and sent to your pH sensor immediately. You have cells in there, and it's a very, very complex medium that's changing very, very rapidly. We want to have a like for like scenario. We want a representative sample, and the pH changes very rapidly. And then in between samples or calibrations, we always want to clean the sensor and blot the sensor with like a Kim wipe. We don't want to wipe the sensor. Wiping the sensor creates a very micro type cracks. And then with that, within the pH side of things, when we have proper sampling techniques, then we know that our inline pH sensor is actually working correctly. So if we know that we're outside of our specified range, we know then that our acid and base addition is actually accurate. So again, as that follow-up recap, everything that I kind of talked about, the inline pH, selecting it, the type of way that you're sampling, running it to your benchtop meter will help solidify a proper acid base addition strategy. And then again, really at the end of the day, I strive to really make your guys' day easier. I don't get paid or anything for this. This is something that I just do to truly help you guys optimize your bioprocess. And if you need more technical side of things of pH, like how a sensor creates that millivolt charge, or more information on the temperature side of things, or what is the measurement principle, I have a link here on the bottom. You can go to Google and type in Hamilton pH video. It's a very nice 12-minute video. I highly recommend you taking a look at that as well. So at that, I will end it. Thank you again so much, Hamilton, for letting me present on this platform. I'm really excited to see if I helped anybody out. So thank you.
So Fred, everybody's still there, so very interesting. I can start with the Q&A, which are already there, and they started during the presentation. So some of them for topics that you have covered later on. So let's start with congratulations with some people for your family. The newborn. Then the real questions. Will we get a copy of the slides and recording afterwards?
So this will be on Hamilton's website, if I'm not mistaken. It's what recorded and will be on Hamilton's website. If you need a copy of the presentation, you can contact your area sales manager from Hamilton, and we can do that on a case-by-case basis.
Yes. Second question, would you recommend open junction pH sensors for online bioreactors measurements?
So I would need to know more about your bioprocess before recommending one or the other. But mainly the customers that are getting the best results would be a ceramic junction. The open junction is a little bit of a higher maintenance type sensor, but it's really meant for the laboratory side of things, or anything that doesn't have tris sulfides or proteins in it. I would personally, for most, and again, I'm making a general statement here, most bioreactor in situ upstream, I would recommend a ceramic junction sensor.
Then, what is your personal opinion about 3-point calibration? Example 4, 7, and 10.
I like it. If you only are running a bioprocess and you know your sample is going to be between 5 and 7, there's no need to run that 10-point. So you can run just 4 and 7. It's really all depends on where your sample is. You really, again, want to make sure that you're bracketing it. So if it's below 4, I don't recommend the 4, 7, 10. I wouldn't even recommend 4 and 7. I'd recommend, again, that 1.68 and 4. But 3-point calibration, the more calibration points you have that's in that bracketed range, the more accurate you're going to get more than likely.
Okay, I jump to another question which just came in just because it's a little bit the same topic. Do you think that measuring pH at one point in an industrial fermenter is enough for proper pH control with acid-base addition?
So did I hear that right? The question is, do I think it's acceptable for just a 1-point calibration?
No, sorry, it was my error. It's not the same topic. Measuring pH at one point in an industrial fermenter is enough for proper pH control with acid-base addition. It's not calibration, sorry.
No, I mean for 1 point, for any sort of acid and base, and again, I might need some more clarity on the actual question, but really at the end of the day, if it's a calibration or a point to point, the more points you have is going to be the most accurate, I guess. I'm still quite a little bit unsure of the question, but really at the end of the day, you really want to have your sensor bracketed from the expected sample. And then within a product calibration can be a 1 point. That's not a problem. That would be adjusting the internal slope of your bioprocess sensor that's in situ. So you've already done a 2-point calibration on your in situ pro, but that product calibration will then help that.
Okay, next question. How do I know if I have a single junction electrode as the brand information is not mentioning it, although my electrode reference change color fast, black, after start using?
So if you're starting to see that black material, if it's inside the sensor, that's usually a single junction sensor. You're getting silver bicarbonate that's forming inside the probe. So you're seeing a deterioration of that reference wire. But it also, I would probably guess that that's an epoxy body sensor, where it's probably either a wick junction, or what they call like a glass fiber junction, and it's not meant for this application. Usually, if you see this black coating that's happening, it's usually a coating. And you would want to first try like a Pepsin rinse, like a 1% Pepsin and a small concentration of HCl, heat it up to about 50 degrees centigrade, put your sensor in there for roughly about 15 minutes, and then keep that in storage solution for 24 hours and see if that's helped.
Okay, then another question that I guess you already went through, but anyway, I read it. How do you know when to replace a pH sensor? Can you make that judgment based on offset and slope value, or maybe response time? And how would you recommend to determine response time?
So it's application specific. So with response time, if there's a lot of people that are running the laboratory pH probe, you want a faster response time. But if you're the one that's running the sensor and you did the calibration and it took 30 seconds for it to calibrate on pH 4 and pH 7, you want to wait for at least a minute now on your actual sample itself. You want to double that response time because your buffers are going to be the fastest responding possible. But if you have a lot of customers or a lot of people in the lab running this, you really need a fast responding sensor. Regarding the other statements that were mentioned, I do the calibration, I bracket the sample range, then I do a check based off your SOPs. So if your standard operating procedure is that you're plus or minus 0.05 or zero point 0.1, you want to make sure then once you've did your calibration, you're checking a buffer to see if you're within that range. If it doesn't, if it if it's outside that range, then you need to run another calibration and see again the precision to see if it's working. If it's not, you probably need to replace that sensor.
Okay, could you get a slope higher than 102%?
Absolutely. Most sensors will degrade down but in certain situations they do degrade upwards, and that's why we recommend 102 to 95. But certain applications you do receive a higher slope. Not usually. Usually when the reference is deteriorating, it's going to lower the interactions between the 4 and 7 or 7 and 10 compared to theoretical. So that number that you're going to be seeing between 4 and 7 is going to be smaller and smaller than 177.6. So you're going to see a decrease in slope. But there are certain standards that it does get higher than 102. But again, make sure when you're doing a calibration, I really want to make sure this hits home that you're not just utilizing the percent slope to determine if your sensor is working efficiently or not. It's really that secondary check within the buffer to see if it's reading the buffer correctly. Because if it's reading the buffer correctly, you know then it's going to read your sample correctly. If it's not reading buffer correctly, you know there's no way it's reading your sample correctly.
Another question. We have still questions. I want to reduce workload in our facility. I understand it is recommended to calibrate after and before autoclavation. Can I skip the one before autoclavation?
No, in my personal opinion. So within autoclavation, after autoclavation, you're usually only going to be able to do a 1-point calibration. Outside of calibration, you're going to be able to do a 2-point calibration, and then of course you have that autoclave shift. But I highly recommend, highly recommend calibrating the sensor before autoclavation as well.
Okay, we currently clean our probes with 0.1 normal NaOH. Why do you recommend hydrochloric acid for cleaning?
An acid or a base rinse is totally fine. For me, I've just always used, I guess, in my formal work, I've always used HCl, but I do know a bunch of customers that utilize sodium hydroxide as well. Just, really at the end of the day, take a look at the owner's manual of the sensor that you're utilizing. But for me, it's a personal preference. I use HCl, but, you really want to make sure that you heat that up as well. But I highly recommend, again, utilizing the manufacturer's cleaning protocol first. And then if you don't have their cleaning protocol, you can use the 0.1 NaOH.
I ask assistance for this question because I don't understand. During troubleshooting, you said to test the pH meter for 0. Do most have a pH meter? Okay.
I'm assuming you're asking the question when you're doing the self-diagnostic test on the pH meter. So most pH meters have a B and C connector on the back end. It's usually the universal connection of the benchtop meter. There's usually a cap on the back end. If there's not, you can Google benchtop pH meter shorting cap, and you can buy one. But you want to plug that in, and the meter should read 0 millivolts. So change your meter if you don't see millivolts on the display. Change it so you can. Every pH meter will be able to see millivolts specifically because that's the unit of measure. And you want to see 0 millivolts plus or minus 0.2 millivolts. If you see 1 millivolt or 2 millivolts, that's too high. That just means that when you're collecting the millivolt signal from your sensor, your meter is not reading millivolts correctly. So that's a quick diagnostic check.
Coming back to a 3-point calibration, how does it actually work? Are 3 points used for a single calibration function, or are actually 2 different calibration functions generated with the intermediate pH calibration being identical?
Great question. So the newer pH meters, they do actually, so if you do a 3-point calibration, it will use the individual calibration for the 2 points. So if you run a calibration, let's say between 4 and 7, and you get and then let's say 7 and 10, the traditional 4, 7, and 10, the overall slope, let's say, is 96%. It will spit out that value. But internally in the probe, and some of the meters, you can actually go into the software and see the individualized slope. So you might be from 4 and 7, you might be at, let's say, a 98%. it's going to use that specific slope. It's not going to use a general slope that it gave you, that percent. And then also with 7 and through 7 and 10, let's say that's at like 94% or 93%, it will be utilizing that specific slope, not the 96 per se.
Okay.
And then I
Most
guess
of
add that really quick. Sorry. Some of the older meters will do the general slope of the 9. It will average those two together. So it's really, really key to make sure that you ask your manufacturer of the benchtop meter on how it's utilizing that. But most of the newer benchtop pH meters are taking the 3-point calibration and splitting them up into two individually percent slopes to measure your sample on.
most of my customers use the Emerton EasyFirm Plus. Is this a ceramic double junction sensor?
Yes. So the EasyFirm Plus would be a double junction sensor. Is what they call an Everett F junction. It's a ceramic. It's a protected junction where basically it helps eliminate any contaminant to affect the actual reference wire to maintain that reference solution in there. And then the junction is a ceramic junction. It's a very good sensor.
Okay. How often can you sterilize pH sensors without worrying about the quality of the measurement using high temperature glass and ceramic junction sensors?
There's some sensors that it will not even work one time. Some sensors you'll be able to sterilize a few times. Some sensors you can sterilize 10 times. Really, at the end of the day, take a look at the manufacturer's protocols, see what they can handle. But a good thing to do at the end of the run is to check how your pH sensor reads buffers. If this is a question that you do have, that you think that your pH sensor is not working, at the end of the run, put it in 4 and 7 buffer and see how it's running. And you can do that on your control tower. And that's very easy to do. But that would be what my recommendation is. There's, again, hundreds and thousands of pH sensors out in the market right now. There's tens of sensors within for the bioprocess. I can't say one number or not. That's the problem with pH sensors is I wish I could just say, hey, yes, it's going to be 15 autoclavation cycles. It just doesn't work that way. And even the same manufacturer, based off your process that you're running, one sensor might run 14 times, the next one might only run 7 times. It's really understanding how your sensor is kind of degrading, and it's really important to take the calibrations as seriously as possible.
Okay, how can you explain pH difference between different brands after calibration, new sensors?
The differences are glass type, reference type, and junction type. There's a lot of sensors out there, and as I showcased today, I just showed really quickly 3 different glass types, 3 different junction materials, wick, ceramic, open junctions, and then really what type of references is it a single, double, or trio type sensor, and these are kind of the major differences that you can see, and each one of them are going to calibrate a little bit differently, faster, a little bit more accurate. If it's a refillable or gel filled electrode, there's a lot to go in when utilizing a sensor. So if this is a question you do have, based off what your application is, one manufacturer might be better than the other, or multiple manufacturers might be okay for your process. So if you have more questions on that, definitely reach out to your Hamilton area sales manager, and then they could always give me a contact, and we can do a one-on-one call. I'm fine doing that.
Okay, Fred, again on the 3-point calibration. So 3-point calibration, 2 slopes, then 2 buffers for verification will be required for being compendial to USP.
That is correct.
Okay.
So you would want to then measure in a 4, and it would be on the axis. So a lot of people try to go away with that, with just picking 7, because 7 itself will be hitting both points. But really, to be fully compliant, you should do the 4 and the 10.
Okay, then let's go back to the one point of measure, not calibration, one point of measure in the reactor. Now we have the explanation. For instance, in lactic acid bacteria production, you have huge pH changes in a short period of time. Measuring pH only at the bottom of the fermenter while adding ammonia from the top might not ensure an homogeneous pH value in the whole broth because of heterogeneous liquid distribution in industrial bioreactors. So adding several pH sensors might improve the actual pH value through the bioreactor, not only relying on the measurement at one point.
Yeah, so I mean, if you within that application, if you have one on the top, so if it's small scale, let's say it's a 5 liter bioreactor. A 5 liter bioreactor is usually going to be a 325 millimeter sensor based off the model. It could be higher or longer or shorter. But then you can also use, let's say, like a 120. Again, the biggest thing is to make sure that the sensor's immersed, but that's also a really good study to see how it is mixing. Because if one is a lot higher than the bottom, you're going to be able to see that change. But of course, that's something that you would have to determine on yourself, not to. I can't make that recommendation on your end. That would be probably process specific.
Then Polylite Plus can be sterilized, also autoclavable.
I believe so.
Did you hear me, Fred?
Is that Did you ask, can the Polylite Plus and the Easy Firm be autoclaved and sterilizable?
Polylite Plus, if it can be sterilized and autoclaved.
I believe so.
I don't even remember. I guess it depends on the glass.
Exactly.
I will check in the meantime. I have another question. We usually use your probes one time. Do you have any recycling program where we can return probes? And if so, can we get any credit for
So that would be something that Hamilton would need to discuss with you. I'm not affiliated with Hamilton, so that might be something you might want to bring up with your Hamilton area sales manager and work with them directly.
them? Okay, let me check for the polylite. I don't remember. Yes, it depends on the glass for the autoclavation and the sterilization. Yes, anyway, you can ask your RSS manager, which is the best sensor, for your use. Okay, so the questions are over. Oh, no, one more. What about calibrating with pH 7, so the isoelectric point? Do you have a limit for this offset or to judge on sensor replacement?
So within the isoelectric point, basically you're taking temperature out of the equation for the most part, the temperature effective error. Um, Basically the offset itself, it's based off what your application specific is. So with certain customers, we see, plus or minus zero point 0.2, some are plus or minus 0.05. The one thing I will stress though is the accuracy of the full system with the pH meter, the sensor, the buffers, the way you run the sensors. You shouldn't have anything that's tighter than plus or minus 0.05. That's like running the system almost perfectly.
Okay. So Fred, a lot of questions we had. We also have a lot of attendees still there. Okay, thank you everybody for attending. I've seen a lot of interest. You will find the presentation in some days on our website, the same page where you did sign up. And yes, thanks a lot. Thanks to you, Fred, and stay tuned for next webinars.
Thank you so much for having me. Thanks, everybody.
Bye bye. Bye bye.